Hi everyone, it's Shamila here from Can Do Teach, and in this video we're going to be talking about surds. So surds are one of those topics that I've seen make a lot of students cringe, but actually once you get to know them, they're not that hard. So I'm hoping to show you in this video how to deal with surds and that they're actually quite straightforward. So surds are a type of number that are irrational, and specifically they're the irrational numbers that come out of doing square roots. So square roots or cube roots. Anything like square root 2 that can't be simplified further. So for example, square root 4 is not a surd because it's the same as 2. But anything that's a square root of not a perfect square is a surd. Alright, so let's start by talking about estimating surds. So while we don't immediately know how big square root 5 is, we can figure it out pretty quickly if we know our square numbers. So it's worth knowing these at least up to 10 or 12. And so what you do here is say that, well, 5 is in between 4 and 9, which means that the square root of 5 must be between the square roots of 4 and 9. So it must be bigger than 2 and less than 3. So square root 5 would be equal to 2 point something. So we can just say 2.5. Alright. So then we can do the same thing with square root 70. So 70 falls between 64 and 81, which means root 70 would be 8 point something. Okay. And again with square root 55, it's between 49 and 64. So square root 55 would be 7 point something. Okay. So I don't know about this 5, it might be 7.4 or 7.9, but it's definitely between 7 and 8. So I'm just estimating by just picking the number in the middle. So why do we need to estimate surds? Well, the reason we use surds is because it's an exact representation. So we know that if we try and write a surd or any irrational number in decimal form, it has infinite decimal places. So if we write it as a decimal, we always have some error. We can't represent it exactly. So that's why we use the surd form. But there are some cases where it's more useful to have an approximate value that we can make sense of than an exact value that we don't really know what it means. So for example, if I'm looking at a square and I know the area is 55 meters squared, it's more useful for me to know that the sides are approximately equal to 7.5 meters than knowing that they're exactly equal to square root 55 meters. All right. So now when we think about doing operations with surds, we can remember that actually the square root sign is exactly the same as a power of 1/2, which means that we can use all of our index laws on surds. So if we look at this first example, square root 3 squared, we know that the square root and the squared cancel out, either by definition or because the square root 3 can be written as 3 to the power of 1/2, which squared means that these cancel out because they multiply to give 1. Alright. Now these ones, when we're adding surds, again we look at like terms. So if it's the same surd, we can add those together. And so we've got 2 of root 3 and 1 of root 3. So in total we've got 3 root 3 here. So it's important that the surds look the same. So that's why it's important that we simplify our surds, which we'll see in the next slide. Okay. Then when we're multiplying surds, just like with index laws, since these have the same power, since they're both square root, we can multiply the insides as well. So we can say that that's one big square root sign over the 3 times 7, which means that it's the same as square root of 21. And so that can go either way, right? Depending on how we want to represent our surd. Same thing goes for division. We know that the square root, or the power of a half, can be distributed over the division. So we can change that to being square root 4 over square root 9, which we know simplifies to 2 over 3. And finally, if we've got something like fifth root of 32, if we know that 32 is something to the power of 5, then we can cancel that out. So in this case, I know that 32 is the same as 2 to the power of 5, and the fifth root of that would cancel out the root 5. So you can also write that as 2 to the 5 to the power of 1/5, and that would give me just 2. Okay, so that kind of shows you how you can apply all of your index laws to surds as well, because we know that they are equivalent. Okay. So as I mentioned in the previous slide, it's important that when we write surds, we always represent them in the most simplified form. Otherwise, it can be difficult to tell that two terms are like terms. So when we simplify surds, what we want to do is take any perfect squares outside of the square root. So if we look at this first example, 3 root 200, I can notice that the 200 has factors 2 and 100. And this is important because 100 is a square number. It's a square of 10. So I know that I can split the square root over the product. So that's 3 root 2 root 100. Okay? And root 100 is actually just equal to 10. So it ends up being 3 times root 100, which is 10, times root 2. So I could just write that as 30 root 2. Okay? And now because there's no perfect squares left inside the square root, that means the surd is completely simplified. Alright? So if we look at what happened here, I can kind of skip these two steps and just immediately say that since this was a square, it comes out and multiplies the coefficient of the surd. Alright? So if we look at this example, 84, you may recognize immediately that 4 is a factor of 84. So I can say that that's 4 times 21. And now 21 can be further factorized into 3 and 7. But since neither of those are perfect squares, we'll end up recombining them. So now we go through and say this 4 comes out of the square root as the square root of 4. So we end up with 2 on the outside. And then 3 times 7, since there's no more perfect squares, we just multiply them again. And we get 21. So 2 root 21. Okay. And looking at this example finally, we know that the square root can be distributed over the two things. So square root 9, square root 75. And now the 9 straight away simplifies to 3. The 75 has factors 25 and 3. So since 25 is the square of 5, we can pull that out. And we're left with 5 root 3 over 3. Okay, so that's how you simplify surds, and you know it's completely simplified when the numbers on the inside no longer have any square factors. Alright? Okay, so the last thing we need to look at is rationalizing the denominator. So far, all of the simplification we've been doing of surds has been so that we can recognize when terms are like terms. So the same goes for these ones where we have to rationalize the denominator, because when there's a surd in the bottom, say I'm adding it to square root 2, it's not immediately obvious that I can add these two things, because from this form I can't tell that this and this are like terms, but in a second we'll see that they actually are. So the standard convention is that surds aren't allowed to appear in the denominator of a fraction. So anytime we do have something like this, we have to rationalize the denominator, which means make the bottom number rational. So the way we do that is to multiply the top and the bottom by the square root 2. So what that gives us is on the top, we get a square root 2, 1 times square root 2. And on the bottom, we get root 2 times root 2, which is just 2. So now we haven't actually changed the number because we multiplied the top and bottom by the same thing. But the number on the bottom is now rational, so we have rationalized the denominator. So it's clear now that this and root 2 are like terms. So let's say we had 1 over root 2 plus root 2. We can't tell that those are like terms, but if we've got root 2 over 2 plus root 2, then we can see that, oh yeah, they're both just multiples of root 2. So it ends up being 1.5 or 3 on 2 root 2. All right? That's why we have to rationalize the denominator. So we'll do one more example. So here, the important thing is always the one on the bottom, not the one on the top. So we still have to multiply top and bottom by root 3. So we end up with root 3 times root 3 is 3. Root 7 times root 3 is root 21. And we're done. So things get a little bit trickier when we have something at the bottom which is actually not a pure surd. It's a sum of two things. So 2 plus root 3, for example. And so what we do here is we actually multiply not by just the root 3, but by the conjugate of the denominator. So what conjugate means is that we have the same thing, the same two terms, but rather than having a minus between them, we have a plus. So if this was a plus, then this would have been a minus. Okay? And again, I have to do top and bottom the same. So 2 plus root 3. So the reason that we do it like this is because now when I expand this thing, it ends up being a rational number. So let's actually try expanding this. So on the top, we simply get 3 times 2, which is 6, and 3 times root 3, which is 3 root 3. And on the bottom, we have to do our FOIL expansion. So we start with 2 times 2 is 4. 2 times root 3 is 2 root 3. Negative root 3 times 2 is minus 2 root 3. And negative root 3 times positive root 3 is negative 3. So we see that these two middle terms cancel, and that's the irrational part. So I end up with just 4 minus 3 on the bottom, which is just 1, and 6 plus 3 root 3 on the top. So I've just got 6 plus 3 root 3. And I can factorize the 3 out if I want. So 3, 2 plus root 3. And we're done. Okay, so that's how you rationalize the denominator, whether you just have a pure surd in the bottom, or if you have a sum of surds or non-surds. So to summarize, surds are just a particular type of irrational numbers where the square root sign can be represented as a fractional power. So you can use all of your index laws to apply to surds as well. Okay, and the important thing is to simplify them. So you need to represent surds in a way that you can compare them so you know when two terms are like terms. So that can be achieved by factorizing the number inside the square root sign and removing any perfect square factors. And finally, if you have a surd in the bottom of a fraction, you need to rationalize the denominator so that, again, you can compare like terms. So I hope that helps make sense of surds and make them a little bit less scary. If you have any questions, please write them in the comments below. Otherwise, you can always get extra help at candoteach.com. Thanks for watching, and I'll see you next time. Bye for now.